Hi everyone, thanks for joining this webinar today and appreciate your time. I understand there's a lot of these things that are currently out in the market asking for your time, so I really appreciate the time you're giving us to come and listen to some of the new technologies and some of the new things that we're currently undergoing at Glencore Technologies. So I'll just begin. I'll start to share my screen and start to run through our presentation. So just a bit of a background. So the idea today is we're looking at the mineral processing suite that we offer. So we'll be looking at the Jamison cell and also the ISOMIL technologies. So I will start now. Okay, so basically, I'll just give a quick overview of Glencore technology and where we sort of sit within the business. So we are based in Brisbane in Australia, and we have approximately a 40-year history. We're a part of the larger Glencore group, and we offer 5 core technologies which were developed within the Glencore operations, and we offer them to clients around the world. So we have a global footprint, and we execute projects across many regions around the world. And we also have access to operations, which gives us a very unique technology transfer model. So we have the ISOMIL technology, the ISOSmelt and ISOConvert. We have the Hydromet Albion process, the Jamison cell, and also the ISOKID technology. So these are the main ones that we offer as part of our group. So for those who don't know, this is really just a snapshot of Glencore as a global company. Within our group itself, so GT or Glencore Technology, so representatives in these various parts of the world. So today's discussion, today myself, Glenn Steeper, I'll be talking about the ISOMIL technology, and really the main topics I wanted to cover off are the importance of bubble size, the cell upgrade performance, so some very unique, some very interesting things I hope you'll find in terms of rougher performance in particular. Some of the coarse and fine particle performance, which again is a few myths in the market around the sort of particle size, what the Jamison cell can actually float. So I wanted to have a bit of a chat around that. Also, the reduced footprint benefits. So a bit of a case study I also wanted to discuss there. Some recent achievements and also some recent installations. And some of those achievements, you'll see there's some new launches of some new products that we want to have, and then how that sort of fits within the market and can offer some very big benefits that we believe going forward. And also just the accuracy around test work to full size scale up. So again, just want to sort of show how accurate that is when it comes to actually sizing equipment. The second part of the presentation will be run by Jon Garnett, and he will be looking at the ISOMIL technology. In that, he'll be having a quick look at the ISOMIL, just operational overview, also just the superior size distribution, some recent projects that we've executed. There's some new designs and footprint comparisons, developments around wear, and also some power reduction research that we're currently undergoing as well, which is looking very promising. And again, on the similar vein to above, there's also the SIG plot, so the full-scale accuracy, where we believe we have quite a unique position in the market where we offer very, very high accuracy upscaling potential. And then also just some general information around there as well. I'm just going to share a point, as you can see where I'm pointing. Oop, wrong way. Okay, so I'll begin with the Jamison cell technology. And just a quick overview of the market. So as you can see here, we currently have 380 installations, and to be honest, we actually just had another sale today, another PO just received, so that's potentially 381. So most of ours are obviously across a lot of different commodities, copper and coal being our largest one. We've actually seen a lot of growth in the last few years, which is really, really good for the technology. I think there's a lot of people in the market that are finally sort of understanding some of the benefits that the Jamison cell actually does offer to basically all commodities. So I'm hoping that this presentation will start to show some of those recent achievements and some of that information that's now getting out to the market. And I believe there's the reason why we're seeing this large growth. And here's just a map of the global distribution. So if we just, this is just a couple of quick slides. I don't want to sort of dwell too long on this. This just sort of looks at some of the basic principles of the bubble size versus the rate constant or the recovery. And this is just a basic silica application. And what we see here is, as you see the bubble size decreases, this is the increase in recovery. And you can see here that there's a huge difference between even halving the bubble size as to almost doubling the rate of recovery. So if you look at the actual sizes themselves, you can see here that the Jamison cell sits right down in this 0.5 millimeter zone. And if you look at the conventional mechanical or even your column cells, you can see why that is, that the Jamison cell gets that extra performance. So that's just sort of a basic principle. It's really one of the fundamental principles and advantages that the Jamison cell has over these other technologies. It's that very fine bubble size, gives that high surface area, and makes sure that you get that really good recovery. And it's also, it doesn't matter about the size of the particle, because it's shown that at that size, it recovers, as you'll see in the next slides, all spectrums of the particle sizes. So now I wanted to just roll into some quick performance examples. Now, some of these are currently installed, or some of them are very close to about to roll into actual projects in terms of orders. So I'll start on the first, on the left-hand side over here. Now, this is a project that we're hoping to proceed into in terms of an order within the next potentially 4 weeks. And this will be the first of its kind in terms of our new launch of our new Z cell. Now, what the significance of this these findings, if you look at the top one is gold and the bottom one is copper, these black dots here represent 100 cubic meter tank cells. And there's basically 7 of these on a row. So these are installed. These are based on survey data at the same time that the Jamison cell was running its large pilot demo scale L500 off the rougher feed. So you can see here, just to give you an indication, it's 0.25% copper is the feed, so it's very low. It's high tonnage and low grade, and the gold is around 0.7 grams per ton. Now, what you see here, and there's a bit of scatter because obviously they're running a few wash water, running through different scenarios just to get a feel for where it sort of sits within that grade recovery zone. And you can see here that a single Jamison cell on the rougher feed was getting up around 40 to 50 grams per ton of gold. And then on the copper, you can see, and this is indication of what the final grade is of target. And you can see here that at around about nearly 80% recovery, it's also achieving a final concentrate grade for that single one unit at the front. If you look at the similar performance of the tank cells on the same feed, you can see that the tank cells are only getting an upgrade from 0.25 up to around about 5% copper, and similar with the gold, getting 0.7 up to around 10 grams per ton. So which is typically what you'd expect from a rougher. The difference is that the Jamison cell, because of its very high upgrade potential, is upgrading 5 times as high in this indication, as this application, sorry. It's getting 5 times higher upgrade than what a standard tank cell is doing. So you could imagine that by having this, it means that you're pulling a huge amount of mass that potentially would have gone through the regrind circuit and would have gone into the cleaners. You could potentially take that out to final con, or even if you don't even do that, the point is you're going to be upgrading to a significant amount in terms of reducing the amount of entrainment and gang that you pull across into the circuit. If you then look across here, this is currently installed in Russia that we have. This is in a rough application, one of our large 24 downcomers. And you can see here that the feed grade is 1 grams per ton, 1 gram per ton gold in the feed. And this is actual installed performance. And you can see it's running around about sort of 60 to 70 grams per ton at around 60% recovery. So that's again around a 60 to 70% upgrade ratio, which is very high and significantly high in that first cell. If we then take a look up here, and these are, again, this is looking at a number of our L500, so demo scale plants on various rough applications. So Strathcona, Minto, Tritton, and also Mount Isa. And you can see here the results, again, are very high in terms of the grade. These are some of the feed grades that are coming in. And this shows the grade and recovery curve that they're achieving. Now, what's interesting about this graph, and this is what I'll be talking a little bit more about a little bit later, is the fact that it's very flat. So basically what it's indicating is all the way along here, that as long as it's liberated, it's at the right size, and it's liberated enough to make final con grade, the Jamison cell will take it and it will bring it to that concentrate grade that's required. What you see here is this part that falls off the end. This indicates where you're reaching the non-liberated composite material. So the Jamison cell is very good at identifying the point where you can make good liberated grade product, and it also differentiates the point where you hit that composite zone, where you're starting to get into composites that will not make final grade. That's the material that needs to go to regrind. That's the material that needs to go through the cleaning circuit to get another go to upgrade. So if we then look at the size distribution in terms of the range in which the Jamison cell can actually float, and what we have here is we have an example. This is the Cadia from Millop's paper that was actually produced by them. And if you look here, this is in a cleaning application in a copper gold. And we have two cells here, two columns, one with the Jamison cell and one without the Jamison cell. Now, what I sort of want to point out here is this is the very fine, so we're talking -7 micron, and it's chalcopyrite, bornite, and also your free gold and your sulfide gold. And the big thing is, if you can see here, that the very fine materials recoveries jump from 73% to 94%, 92 to 98, 91 to 96, and 77 to 96. So a huge improvement in the ultrafine particle flotation, which I think most people are pretty familiar with that, and they understand that's what a Jamison cell is extremely good at, is doing ultrafine grinding, ultrafine flotation. What is also interesting on this table, however, is then you start to look at the plus micron fraction, and you start to see 92 to 99, you can see 98 to 99, even 97 to, yeah, it's obviously a slight increase, but it's also floating the coarse material as well. So the particles are fine, are getting extremely high recovery, but it's also doing a slight improvement in the coarse range as well. So if we then look across to the graph over here, what this is showing, this is actual data from Mount Isa in a cleaning application. And if you look at the particle size range, this is a chalcopyrite concentrate, you can see that the actual recovery by size of that chalcopyrite is around 93% at 3 microns, all the way up to 97% at 300 microns. So the Jamison cell itself is actually able to recover basically all spectrums, size spectrums within that concentrate. There's obviously a limit. It's like any other tank cell, 300 to 400 microns is probably where you wouldn't want to exceed, but that's typical of most flotation devices. But the difference is it also has a very strong ability to float the ultrafine as well. So you can get both sides, you can basically cover all bases through that. And if you look down here again, this is data that's also taken from over here, the Cadia, and you can see here right across all the size distributions, right across, you can see the large uptick from the Jamison cell installation. Down here in this table, all this is really showing is these are a number of installations that we have. Polyus, we have it at a rough application. There'd be one in Cadia, Sepon, which is due to be commissioned, and also New Britannia as well. And you can see here, these are just some of the particle size or the P80 feeds that will be feeding into the Jamison cell at the head of the rougher. So it's seen as it can't float the coarse product, but actually we know it's very good actually at floating both the coarse and the fines. Looking now at the footprint. Now, this is an example here that we had at Mount Isa in the copper plant there, and there was a whole number there was some columns in here and a whole number of cells that actually was replaced. And what replaced it was 3 Jamison cells that basically replace most of the cleaning circuit. And you can see here that in this green box here, this was the size of these 3 Jamison cells installed. And this is the material or the cells that were taken out to replace those, by those 3 Jamison cells, which is, in total, it's a reduction of 76% of the surface area, the flotation surface area. So huge reduction, and only for a small size. And you'll see why this is relevant in the next couple of slides, where we start to look at how you can start to look at this as a bigger picture. We're taking the footprint savings and then seeing how you can actually then blow that out into a full circuit. Just up here, this is just some information in terms of plant survey versus the dilution cleaning test. You can see that, and again, I'll talk more about this, is very, very good correlation. It's a 1-to-1 upgrade to full scale from dilution cleaning, and also from our pilot or lab scale work to full scale. So we have a 1-to-1. There's no times 2 or 2.5 or 3 times factor, which you typically get from a conventional cell in the lab up to a full scale tank cell. Again, this is just looking at it from the outside of the building. That's what basically was replaced, and that's the actual installations of the new 3 Jamos in there. Now, if we want to look at just some quick recent achievements, and so there's a Kolawasi one that was recently commissioned just in November last year, and you can see here these are some of the columns that were currently operating, and the Jamison cell was designed to replace that. And what you can see here is the actual data is significantly higher. So if you look at the moly recovery in particular, you can see the columns were only getting around 20%, and now we're sitting up around sort of over 60-65% recovery. And there's even a higher in the copper as well. So a huge benefit there by having that Jamison cell installed into that plant. There's a full Jamison cell design, which I will talk about shortly in the next slide. And the other thing that you may have seen in some of the links, which for us is a really, it's a bit of a game changer, and where we sort of see that what we believe the industry could potentially heading with Jamison cells in it, is a full Jamison cell circuit. So the Hud Bay has placed an order, and we're going in now full design for the Jamison cells in the 2 roughing and scavenger, and also in the clean application. So that's a total Jamison cell from start to finish plant. Some recent installations, we had the Kamoa-Kakula, there's the Sepon, as I mentioned before, Pogo, another rougher application. So Sepon is a rougher, the Polyus is also a rougher. And if we look at the others, Synclinorium, Kansanshi, Carapatina, and also Peak Gold, which is a full cleaner, or has the cleaners scalper and also the re-cleaners as Jamos as well. So I just wanted to now go into talking about something that we're pretty excited about. Obviously, Hud Bay has already started looking at this sort of thing, and we've also now got a number of clients around the world that are testing, starting to test and look and interested in looking at this design going forward. So I use this as an example here, and I'm actually going to fly around the model in a second just to give you a bit of a view of what it is. But this plant here you're looking at now, and this is based off the real data, so real information that we have from site and real pilot stuff that we've ran to give us a feel for how it would actually perform and how we would design the circuit itself. So this one here, this whole plant here is basically 1,100 tons an hour feed rate. It sits within a space of around 41 meters by 19 meters, which is actually smaller than an Olympic swimming pool. So that entire footprint, including the isomills, a regrind circuit there, is smaller than an Olympic swimming pool. So I think when you think about that, how small that really is compared to a plant that can do 1,100 tons an hour, it's a huge reduction in what you would normally expect to have to do. It practically has no downtime because, as most people have operated isomills, have operated Jamison cells would know that there's very little moving parts. It's just basically a feed pump that feeds a downcomer, and that's it. There's no agitation, there's no blowers, So if one of the downcomers blocks, all you do is basically isolate it, leave the machine running, isolate one of the 24 or however many are on there, quickly unbuckle it, clean it out, and then put it back online again. So there's no real downtime at all. But I think another very interesting point when you start to think about this concept is a Jamison cell has extremely short residence time. Basically, residence time means nothing to a Jamison cell because it has a extremely fast within seconds. It's about 100% contact zone in the downcomer. So there is no inefficiencies in terms of a huge tank cell, which has all this massive space and volume, and you've got to have potentially hours in some cases of residence time waiting for that particle air contact to happen. In a Jamison cell, it happens within seconds. It's 100%. There's no bypassing or anything like that going on in there. So it's a matter of seconds in the cell. And then if you multiply that by an entire circuit of Jamison cells, you're talking from through the pumps that you travel through, you're only talking like a few minutes from start to finish. So if you start to consider startups, you start to think about shutdowns, you think about process control, all of these things happen almost instantaneously, or only a few minutes or something. So there's a huge savings in that potential around just that concept alone. So this is the flow sheet you just saw. And what I'm going to do now is just quickly pull up the model. And I just want to show you what it sort of looks like, some of the concepts. So excuse my driving if I go a bit funny, but so the idea here, and there are a number of ways in which we could design this. This is one that sort of has it up high, which sort of matches the design that we're potentially about to launch in the next, or the order we're hoping to receive in the next sort of 4 weeks. This is the design. There are other designs where we could look at lowering this down and actually potentially even gravitating the tail ends, or there could be a lot of ways to lower this down as well. So this is just one example, but of course, an engineering house would have many options that we would absolutely look at working with them to try and make something that works. If you look from the side, I'll just try and drive this across. You can see here, basically you've got everything is combined into one area. You have walkways interlinking. These cells here, as I say, these are basically, this rougher here is final concentrate rougher, and these two at the back end are your scavengers coming across into your regrind mill. And then your 3 here, you have 2 making final con and 1 as a scavenger at the back end, which basically feeds back into the second one here. So this is basically the whole circuit, and as I mentioned before, it's around 1,100 tons an hour capacity rate through there. Okay, I'll close out of that. So if we keep moving through, so as I mentioned, this is just that flow sheet you just saw. Now, if we look at the accuracy of our scale up, I just wanted to go through a few examples that we have. There are many of these. We have many of these examples, and it's the reason why we give our performance guarantee. We give a performance guarantee of a 25% cashback and that can be based on simply a dilution cleaning test from a lab. It doesn't even need to be a pilot run or anything, because we're that confident that it will scale up directly one-to-one. And here's just some examples that sort of shows where it sits on the same curve. So you can see here a dilution versus a pilot. And on this was a copper example. There's a graphite one here. Again, you can see these are the grade recovery from the dilution test. And these black dots here, or purple, this is actually real data from the site. You can see they sit on the same curve. Again, here, this is talc. You can see it's sitting further out here, but it's on that same curve. Over here, up here, this is the copper one. Again, it's sitting within the actual installed circuit versus the dilution. Again, sitting on that zone, and same with down here. So we're very confident in being able to upscale from lab in terms of dilution tests or pilot to full scale. And so, look, some people like to install it on there to run it, but we certainly don't need that to guarantee the performance. if we look at this, this is actual real data. This relates to the first slide where I talked about the rougher going in there. And what I wanted to sort of show is what the information that we generate from a dilution cleaning test and where it sort of sits, and this is the pilot work that sits again on that grade recovery curve, is it highlights a point where basically this material here sits above the final grade, and everything below this point here, this is what we would consider non-liberated material that needs to go into the final, into regrind and then into the cleaning circuit. So this just what I wanted to show. This is sort of how we will design a circuit. Based on this information, we know that this material above here is liberated at this X grind size. We can design the amount of mass pull that would be expected from here and ensure that the Jamison cell is suitably designed for that. And then we know how big or how much material is required down the back end. Now, one of the things that we do know about every plant, and I'm sure everyone on this webinar is also aware, is that it's not always that easy for some places because obviously liberation varies depending on the different ore body. So we've got a number of examples where we're getting really good liberation, making high grade. That may not be the case in every single operation. Some of them may have other things that stop it, some pyrite, or there may be other things that don't allow it to upgrade to that level. But the thing is, even with those sorts of things occurring, the thing is you're still going to get much better washing. The entrainment's going to be removed. So overall, you're still going to get a much better product and a lower mass product coming out of your roughers and scavengers into the next phase of your circuit. So I tried this before, and I will skip this because I couldn't get it to work. It was just an example of how that currently looks. In here, this is just basically an offering of the cells that we now have on the market. There are a couple of others that we have now put on, and as I was mentioning before, this is the Z8500, the 12, the big downcomer one that you saw before, the 1,100 ton per hour, and also the Z65, which is a smaller version, but it's around about sort of 650 to 700 tons an hour. And then we go into our B cells 24, which are around sort of 450, 500 tons an hour. And we work all our way down to the various ones we have on offer. So that's really it from the Jamison cell business. What I will do now is I will hand it across to Jon. I just want to sort of, I mentioned at the start that at the end of the presentation, we will have a Q&A session. Now, what I really encourage you to do is post any comments, questions you have. And we have a panelist group at the back who's within our colleagues within the Mineral Processing Division. And they will be looking at those questions, and we'll try and answer those at the end. So I'll now hand this across to Jon, and then we'll talk again at the end.
Okay, thanks, Glenn. Let me just share my screen. Here we go. No worries. Glenn just took you over the Jamison cell technology, and I get the pleasure to explain the IsaMill side of the business. A little bit of background behind it. We have 130 IsaMill installations all over the world. These are spread primarily across 10 main commodities, with the most popular being lead zinc, which was the original Mount Isa Mines MacArthur River installation, the platinum group metal installations, which are down in South Africa, and quite a lot of copper gold. Of these 130 installations, the most popular design is the M10000, which accounts for about 50% of these. One of the main reasons why I wanted to show you this graph is actually the one in the top right-hand side. Of the IsaMills, about 14 to 16 installations were producing a P80 of around 7 micron. This is originally the purpose of the IsaMill. The IsaMill was designed in 1995 primarily to liberate the 7 micron material, which enabled the MacArthur River deposit to go ahead and address some of the liberation issues being experienced in Mount Isa. While trying to target this, they were experimenting with vertical mills at the time, and they found that the size fraction couldn't be achieved using this technology, and if it could, it would disrupt all the chemistry within the process, so they had to try and find something with inert media, and that's where a lot of the work was derived. One of the main purposes of this graph is to show you, while that was the original intention of the mill, it was designed as an ultrafine grinding mill. We have expanded a great deal since then, and most of our installations are now over the 100 micron range. I think it's 52. So, how does the ISOmill work? Basically, we treat a P80 of F80 of 300 to 400 microns with a top size of 1 millimeter. Now, that is what we're currently saying out to market. That's what we can treat. However, the ISOmill can treat higher than that. A lot of this is highly dependent on your media that you use within the mill. When this test work was done, we were limited to 6 mil. 8 mil media is now available, and certain installations do that, and we have the possibility of treating coarser material. The mill itself, how it runs, is we try to feed slurry at between 50 to 150 kPa at 10 to the ISOmill. Inside the mill, we have 8 discs and a rotor, and these are spun at a fixed speed. The tip speed of these discs are about 20 meters per second, and as this stirs, it agitates the contents of the mill. To try and break up the material in the mill, we've added ceramic media, which is typically around 70 to 75% filling inside the mill. It should be noted that your media load and power draw is depending on the power draw you're trying to achieve. So some mills will have more media than others. As the media sits in the mill, it's agitated, and this media and slurry is mixed in suspension. As you can imagine, at that speed, a lot of centrifugal forces are in play, and that starts pushing your coarser material and media out to the edges of the mill and allows your finer material to go through the kidneys or the holes you can see in the diagram. As the finer material goes there through the holes, the coarser material goes to the outside, and the rotor back pressure will keep it inside the mill so you can't short circuit. One of these designs is, if you look at the gaps between the discs, it's pretty consistent until you get to the last disc and the rotor, which, if you can see my mouse, is just here. The difference between the two, that disc and the rotor, creates that back pressure, which is helping keep the material within the mill. This is primarily the reason why we have the internal classifier there, and allows us to run an open circuit and reduce overgrinding. One thing that on this design, which I should note, is we work a lot with our clients and what they're trying to achieve. So the internals of a mill can be very different between site, and it's very site dependent. We try to maximize the components and wear life within the mill. So we put small diameter discs, different rubbers in, and we try to do that to make sure that the client gets the most they can get out the mill with the fewest, with the highest availability. A lot of stuff like this can be such as configuring a mill to a high flow mill to try and get as much through as you can, or trying to increase the power, such as we're doing down in South Africa, Anglo-American. Now, that rotor is one of the key things behind the ISOmill that allows you that classification. So that rotor is creating consistent back pressure, and it's keeping the coarser material within the mill. By doing that, it allows us to create a much sharper cut for the mill, which is the CSI, which is our P98 to P80 ratio. This is quite fundamental. Leading into the design of, for example, the Albion process, it was determined you want to have a very consistent particle size, and you want as sharpest cut as possible. A lot of technologies were investigated, ball mills, tower mills, ISOmills, and it was decided that the ISOmill was the better alternative because it produces the most uniform material and had the sharpest cut size. Now, this test work got done several times, and one of the key things is when we do the test work on the lab scale, it then scales up to the real world. And this is a big thing which you don't get on certain technologies. You want the test work to replicate what you see in the field. The example on the right here is showing how the same lab test between SMD and an ISOmill can show you the same on a lab scale, but when you took it up, different technologies will not have that same efficiency and scalable factors, and then you'll get a lot wider distribution. While in a leaching application, this is quite necessary, that you want the sharpest cut possible, and as you can see, certain sites have actually put ISOmills in to try and replace these. Now, I thought it'd be good to talk about some of the projects we did last year, because it just shows you the variety of what we've been doing and what we do and what we supply. Woodlawn is a really good example. Woodlawn was a mill that's a dual duty mill. We only supplied the mill itself, and we're grinding from F80 of 75 down to 30 micron. Now, the mill has two capacities. The mill will run in a tailings retreatment mode when the site's running in that, and we've designed the mill for that case. And then when they swap duties to go to underground, the mill then regrinds concentrate. We had similar specific energies. We worked with the client, and we delivered a mill that could handle both situations. It should be noted that when we were doing this, we were working with ephpCMs, dealing with site, and trying to get the best product for the site itself. Minster B2 was a recent installation as well, which was the simplified plant supply. Now, that was an M10,000, and we were grinding from 107 micron down to 74 micron for a gravity separation tails regrind for a tin operation. Now, this is a really interesting site because typically we've heard comments that that's more a ball mill application. However, the reason why the isomill was chosen is because the site specifically wanted that sharp cut size. They didn't want to over grind, and they felt the isomill was the best technology to do so. And as part of this installation, we worked with site, we provided the ISO control system, and it was all done at altitude, which was a good project, and we've heard a lot of feedback from site that it's running quite well. The other site, Hell Gold, which is an interesting one as well, is more the leaching duty. The M10,000 was installed as a simplified plant supply, so it was everything with the mill, and it was grinding from 43 micron down to 13. This isomill, the intention of the isomill to go in was to replace 6 SMDs. The purpose of this was they were finding that the SMD couldn't actually produce the correct P80 and was having high availability issues and that wide variety in this ratio between P80 and P98. So the isomill was selected to try and sharpen up that cut size and achieve the right grind size. And of note, we've had a fair bit of success with that. And Actaguy is a really good example of showing how coarse the mill can go. So 2 M10,000s as grinding plants were supplied with an M100 for a multi circuit. And we're grinding from 220 and 174 microns down to 25 microns. The site was happy with the installation that they decided to go one step further and order the same thing as the second stage in the expansion. One of the things that I'd like to clear up on this area as well is looking at the size, the F80s. The isomill, like I said, can treat a F80 of 300 to 400 micron. Over 50% of our installations are over that 100 micron mark, and it can quite comfortably treat in this range. A lot of this is highly dependent on your media that you choose. So we can operate in this range, and we have a fair bit of experience in this area. I'd like to also share with you some of the key, more interesting commissionings that we have coming up. We're meant to be now, but in the near future. We have the first M15,000 sitting in Alaska right now. That is in a quaternary grinding application, treating 150 micron down to 65 micron. This is a high flow mill application, and there is a lot of confidence, and we feel this was the right duty for the application. This will be the first M15,000 and will be of some success, we hope. The next one is coal tailings. We have another project in Corbin where we have 2 M1000s and 2 M1000s and M5000 used to grind coal tailings to sub 10 micron. Both these projects unfortunately have been delayed due to the COVID-19 situation, but hopefully they'll be resolved by the end of the year. Now, when talking to lots of clients and we in ephpCMs, we note there's a little bit of misinformation on technology, and we would like to use this presentation to talk to you and try and clear up any confusion and address any inquiries you may have. One of the things that we would like to show you is recently this year we introduced the M7500, which has 2,200 kilowatt motor. The idea was we wanted to introduce that because we recognized from sites and ephpCMs that we had a gap in our range between the M5000 and M10000. And then we recognize that we can't get to sites all the time as quickly as possible. So we're trying to also, due to the COVID-19 situation, we've been aggressive that you saw part of the model Glenn showed. The design, as you can see, is very different. It's a lot lower and it looks like there's a lot less civil work involved. So what we did was we realized that we wanted to make something that was a lot more simpler and more friendly for each site. So we thought we could try and reduce the CapEx costs by moving around equipment, moving the media bin to the side of the mill to try and reduce your civil, your concrete, your steel. We recognized that the mill itself was quite long, so we thought it'd be good to remove the rails so it could be quite small, and then it gave the site the option to put the rails in whenever doing maintenance. And we realized that a lot of supplementary equipment, such as the isocharger water, groundwater tank, could be moved away, and we could just tie in straight into the system. This has created quite a small looking mill, and with a very small reduced footprint. And comparing the equivalent size motor to our competitors, we actually find that we sit in a smaller footprint than what is actually meant. Test work. And the pizza flange test work is basically a controlled materials trial. The idea of this is we want to test different rubbers, polyurethanes, ceramics, carbides, and we want to try and create a product that gives the best wear rates within the mill and also allows sites to increase their power draw and get a better, more efficient grind, and you can go further than originally intended. We've been doing these for 25 years. We have a very strong database of materials tested. We understand quite a different things, and we run these trials quite frequently. And through these trials, we've discovered compounds such as HD60 and 70, which is a lot harder rubber, that have allowed sites to change their operating regime due to the improved wear characteristics. An example of this is at an Anglo-American site. We are doing a trial with these different materials so you get a better life, so you can go up in power and achieve a better grind. The other things we've been doing, which you may have seen a few notes about, and I'd encourage you to come talk to us, is we have been doing a conical spacer trial. The purpose of the conical spacers trial is if you look at the shape of the mill, as the material passes through the kidney, on a modeling situation, we found as it gets close to the shaft, there's actually a loss of momentum in media and slurry and particles. So what we've done is we put these spacers in, and by adding these spacers, you conserve the momentum, and by doing that, you get a more efficient grind, and there's a power reduction associated with that. We did trials on M20s, confirmed on M1000s, which showed a 22% power reduction, and then we're in the process of doing a trial at Anglo American, which is currently on delay due to COVID-19, but the initial results suggested a 22% reduction. Both these are really encouraging and have shown that this is a future where we have definitely got a way to conserve power on site. And lastly, acoustic emissions. We've done a lot of work on producing an acoustic analyzer, which we can put on the side of the mill. The purpose of this analyzer is that we can put an accelerometer up against the shell liner, and as the media hits the rubber on the shell liner, it's producing an acoustic signal, which we've been able to interpret. And by doing this, we can suggest different wear rates along the profile of the mill, get better idea of when to do maintenance. And lastly, which is probably one of the more exciting ones, is on the discharge, we can actually get a particle sizing through some quite complex mass. But this has been really encouraging and is a really interesting area where we've been working on. An area which is really quite important is basically scale up. So we've been doing a lot of work and have done a lot of work in the past with the signature plot process. The idea of the signature plot was to produce a specific energy that would scale up from the test to the real world, and then validate this. From here, you can see we've got sites from Kumtor, Ernest Henry, Mount Isa, Anglo Platinum's retreatment, MRM, and Arium. And what it's shown is we did the test work on the lab scale. We then took all the conditions that we did in that lab, ran it in a larger mill, and it fell on that curve. So the energy we put in energy you put in will guarantee to the same on the real world. And that is something which is quite important to us, and is one of the reasons that's driven our 25% guarantee that we have been doing. This is quite important because in theory, what you should design is what you should see when you actually build the plant, and we have evidence that we do that. Now, we have gone back and looked at previous operations, and when we were doing a lot of early work in 2010, we would take tower mills and we took the original vendor estimates, and we can see a very big discrepancy. This discrepancy shows that the initial things that were done haven't lined up. We have done the work, and we can show that through this test, what we design is what we will install, and this is what we'll guarantee. So going to that, most suppliers offer a maximum about 5-10%. We offer the 25%. This is because of the library tests that we do. We have accredited labs all over the world. We do these tests, and we can give you a good number, and which will scale up. We are an equipment supplier, not an engineering house, so we do offer a lot of technical support to ensure when an installation goes in, we ensure success. We spend a lot of time working, making sure everything gets addressed and works well. This is effectively what we do. I went a bit quicker than I thought, but I might open it up to questions if that's all right.
Thanks, John. What I might do, there's been a couple of questions that have come through. My colleagues in the background have been answering some of them, but what I might do is address a couple of them just now, whilst I've got a bit of time. So there's one question just in regards to the size of the particles that can be floated. I think there was a question around calcite as an example. So what I just wanted to sort of highlight is a similar SG, which is coal. There's a lot of installations in coal, and basically from a coal we float up to around about 1 millimeter. So I think the question was how coarse can it float? Obviously a low SG material, something like coal as an example, similar to your calcite, can float up to a very coarse size. What we tend to say, and this tends to be the golden rule that we always go with, is if it floats in a Denver cell in a laboratory, then it's basically going to float in a Jamison cell. It's the same concept. It's basically producing fine bubbles. Similar in a lab, you'll find it produces very fine bubbles, high rates, high shear rates. That very high shear rate creates a lot of very fine bubbles. It's exactly what a Jamison cell does. It creates very high shear rates, that very high turbulent area where all that contact occurs, produces very fine bubbles and gets very fast recovery. In a Denver cell, you'll notice that the distance between the cell, the contact, and also coming over the edge of the lip is very quick. And that's the same principle within a Jamison cell, which is why it has advantages over tank cells or columns. It doesn't have that space or time where it needs to travel all the way up the column to basically overflow the top. It has the ability to come straight over, produce contact, and then straight over the lip as quick as possible so you don't lose that particle dropping off the bubble. There was another question in regards to how it's controlled. So what I might do is quickly just flick across to my screen again. So do you want to share? So I'll just, hopefully this will work. So I just wanted to quickly show the general way in which you control a Jamison cell. And there's really two mechanisms. That the mechanism is really the level. And basically what you're doing with the level is you're controlling the recovery. The other mechanism you have is actually the wash water. And what the wash water does is it controls the grade. And really those are the two only variables that you tend to adjust within a Jamison cell. One is grade and one is recovery. So it's very simple and very basic to operate and control. There was also I suppose one more question that I just wanted to sort of highlight is that if you go to our website, you'll find that we actually have a number of calculators on there. And what these calculators will do is they'll actually put in some information, some fairly basic information that you have. That information then will be automated into the system. We have some calculations in the background. We'll actually size the circuit for you, the configuration. It'll tell you the size of the Jamison cell or the isomil that you need to put in the circuit to achieve the certain parameters that you're trying to achieve. Now, of course, there needs to be some test work to confirm it, but in general, it's a really good indication of what you can expect and also the number of cells that you can potentially install to achieve that. So I recommend going to our site. We actually have a new calculation which is being launched, new calculator hopefully next week, which is a little bit more detailed. And as you would have seen today, that we're looking at launching the full plant in terms of the whole Jamison cells as well as the isomil. And we actually have calculators in there that will do the full sizing for you. And then what we'll do as part of that is we can send you the test work procedures, particularly for the Jamison cell, which can be done in any lab. And that will then help us to be able to confirm the output of the calculator in terms of its accuracy. And obviously, if it's done correctly and done within a sort of a well run laboratory, we can actually then take that information and use it to go to full scale applications from that. So I think that's the questions that I've seen. My colleagues in the background have been answering questions and posting them. If we don't get to your question today, don't worry. We're recording all your information and your questions, and we will get to these questions and we'll answer them over the next day or two to ensure that we get back to you with something else. So I'll just open it to my colleagues. I sort of can't really see if anyone else is sort of a bit of a learning curve with this webinar system to see if anyone else wants to jump in. I haven't seen any new questions. I can see them, they're coming through, but I haven't actually had a chance to look at them. So I'll just open it to any of my colleagues that want to jump in to answer any other questions. I'll take it as a no. Okay. If you are, sorry, you're mute. Jon?
Sorry, I was just trying to answer them in the Q&As.
Okay. So do you have anything you wanted to add, Jon, to any of the questions?
When we measure granular media consumption in the isomils, we look at grams per kilowatt hour. It can be very misleading if you just look at it on what you'll feed. So this is what we encourage that you measure media consumption to. What else is there? If you have media leaving your mill, there can be a whole lot of factors involved in there, such as overloading the mill, feed flow rate, pressure, the type of fingers you have on the rotor. There's a whole series of things. We have a very good diagram that helps explain where your media will sit in the mill. I can send that through to you, Jarrett. That's right. Those are the main ones I've got here that I can answer.
Okay, so another question that I haven't had much of a chance to look through, to be honest, but another question that has come up in the past, and this is really around the scavenging component of a Jamison cell. There's always been a bit of a, I suppose, I'll say a myth, but a bit of a perception. It's no good for a Jamo, it's only good for high grade, and it's only good for, in a sense, it's, in the past, it's only been for sort of a cleaning application for fine particles. So what we're aware that certain design restrictions may not be, or restrictions, I should say, designs that are in some of the existing cells are not necessarily set up for how we would design it for a scavenging Jamison cell. And a lot of that comes down to basically crowders, having the ability to crowd it in the back end, and also their lip length, and ensuring that we have enough ability to crowd it, to keep it controlled, and also reduce that time required for the bubbles to be formed, the particles, and then to get them over the lip as quick as possible. So these are sort of a couple of the key points that we would always design on the back end, as opposed to how we would design it on the front end. So the different ways in which we would design the Jamison cell and install them for depending on what application it's going into. So I just had a quick glimpse. I don't have any more, I can't see any more questions, but as I said before, what we'll do is we'll record everything and we'll ensure that we get back to you with any comments. So down the bottom of your screen, you'll see there's a Q&A question there. Please post your questions and we'll get back to you. And if there's something here that you wanted to talk more about, either leave a question there, or we will be running other webinars in the next week or so as well that you could easily jump back onto. So again, I'd just like to say thank you very much for your time today and for giving up the hour we've spent with you. So I hope you found it really enlightening, some of the information we've shared and some really interesting stuff. And look, we're really interested in hearing your comments about some areas where you think that maybe we've missed it, or some areas of improvement where we're open and would like to hear your thoughts and comments. So thank you very much and enjoy the rest of your afternoon if you're calling from this part of the world. Okay, thank you very much. Bye.